This week's papers were all about contactless sensing. I'm Matt Rossman, and I'll start by talking about the first paper. The subject of this was using radar to monitor elderly people in their homes. The motivation for this is that as people age, they're at a higher risk of having debilitating health issues, and this could be like a slow decline of their health, or there could be some kind of sudden accident that causes them to require assistance. And so one approach to monitor this is to have a caretaker either in the home or by having the elderly person move into a nursing home. But with this approach, it's inconvenient. You're losing some independence in your lifestyle. So if you wanted to stay living in your home and just have somebody monitor you, well, you could just have a camera pointing at you, but that is obviously not a very privacy sensitive approach. So if you want to live your life normally, then we can use ubiquitous computing to put sensors in your environment and monitor you that way so that you are not aware of the sensing going on, but it is still there. The key contributions of this specific paper is that they were using ultra-wideband impulse radio radar for detecting two things: the vital signs of the elderly people, so heart rate and respiratory rate, as well as detecting abnormal activities like some kind of dangerous fall. So existing technology that we have for monitoring vital signs, we've already talked about the ECG, where you get hooked up to a bunch of electrodes, and that is pretty intrusive. But these days we have technology through things like smartwatches, where it's a lot easier to get those metrics without such an intrusive wearable device. But it still does require you to monitor to modify your lifestyle a little bit by adding this wearable in. So ideally, we have ambient sensing, where the sensors are in your environment. For instance, you could put pressure sensors or microphones in the floor itself to detect falls. There's other kinds of remote sensors, like using cameras and microphones mounted, elsewhere in your environment, or using things like infrared, sonar, lidar, Wi-Fi, and then what this paper does, radar for range sensing. Coincidentally, I worked over the summer on a gait analysis system for assessing the risk of falling for elderly people. So we had a smart floor. This one was very low resolution. There was just one pressure sensor under each tile on the floor. But as you can see, my lab partner is walking along the floor on the top left, and by calculating center of pressure, you can get a pretty accurate trajectory of the person, and you can extract their footstep position and timing, so you can get their walking speed, the step size, which is all very useful metrics for assessing somebody's risk of falling. But this paper was doing radar, and they were trying to do like fall detection at the actual time of falling. So this is the Doppler signature for a fall event. You can see very clearly that spike, and this is kind of the approach that you use typically, is that you create an image from your Doppler data and then get some like features from that image to then do some kind of classification task on. There's a few things that you can measure with radar data. One is a shift in the frequency of the wave that you're getting back. That is like the early approach that was used for respiratory rate and heart rate detection. You can also look at the change in the phase, which is a more complicated and expensive approach, but it is highly accurate. And then thirdly, if you are sending out little impulses of electromagnetic waves, then you can measure the change in arrival time of those waves. And the benefit of this is that you have a large bandwidth, so there's like a really wide range of frequencies that you can measure. So this can capture slower events, which might be like respiratory rate, or much faster events like a sudden movement for like a fall. So the two that are mostly used are Doppler radar and the ultra wideband impulse radio radar. And Doppler can give you very accurately the velocity of a target, but it is a very narrow band, and so it can't really give you the the position of something within that range that it can cover. Whereas the ultra wideband radio, sorry, the ultra wideband impulse radio can give you much more accurate position. So if you have like a lot of people in the room, then you can get the vital signs of like each person in the room. Um, so they also mentioned how camera-based PPG is like another range method for getting vital signs. You can also, using that method, get the blood oxygen level. But the benefit of radar is that it's a lot more accurate for these vital sign measurements. It's resistant to multiple heartbeats and having like obstacles in your environment. And because you're not using a camera, it is more privacy sensitive. So the goal, again, was to measure both the vital signs, cardiorespiratory movements, and then the, the body movements, and do this in some kind of convenient ambient way. This was some of the equipment they were using. You can see the radar module on the left with the receiver and the transmitter. And then on the right is their architecture for processing data and doing classification. This is the architecture of the receiver module. And I don't totally understand why there's this whole hierarchy of like binning going on, like multiple levels of binning. But key things to notice here is this red arrow here, fast time. That's like the time from the perspective of the radio wave as it's like going through your range of your scene. So this axis here is like the range. It's like almost like a positional kind of axis, whereas slow time is like time from our perspective as we're taking multiple samples. And then also there's this axis here in like the z direction because they have a bunch of different samplers going in parallel. And the benefit of that is that by aggregating those results, they're able to reduce the noise. They talk about a bunch of different clutter removal methods. And ultimately they use statistical methods because they are not incredibly computationally complex, and they give you feature extraction capabilities. And specifically in this paper, they used SVD, which I believe stands for single value decomposition. And then the last thing that I will mention is how they get like the body movements and do their activity classification. The main concept here is with Doppler shift, you can get kind of like the big picture movements of something. So this is not a figure from their paper. This is like a different example. But in this example, there is a pedestrian walking onto the road from behind a parked car, and you are in a car driving towards this. So you can see the big picture of like the parked car moving closer to you. You can see that growing Doppler, the Doppler shift going on here. But you might not initially notice the person walking. So this gets into this concept of micro Doppler effect, that as you're walking, like your arms and legs are also moving in different directions. So they're all exhibiting different Doppler shifts. And you can, by like just normalizing your perspective to that like big picture motion, then you can extract the much smaller Doppler effects that are going on. So they had a two-step process. First, they looked for like the big peak in their Doppler signature, and that was like the distance that the person was from the radar module. And then they did that kind of like decomposition and normalization stuff to look for the smaller effects. And that those micro Doppler effects are what they are, is that like it's a unique signature that they can use to track individual people and also detect what kind of activity they're doing.
So once we get the signal from the sensor, we would need to decompose it into the cardiac and the respiratory signals. So this is actually pretty hard because breathing signals generally have a way higher amplitude than cardiac signals because your chest moves in much bigger movements than your heart does. So you end up having one signal basically overwhelming the other, and you don't want that. So one way to break up the signals into its components is using a method called EMD, or empirical mode decomposition. So it's pretty similar to applying a Fourier transform, except when you're doing a Fourier transform, so you would break up the signal into its frequencies and see which ones are the strongest frequencies in the signal. So EMD is basically just a more general version of this, since it doesn't assume that the constituent waves are sines or cosines. So EMD is basically just an iterative method. So it takes the original signal, which is this top graph, and then it tries to interpolate two splines, which are these two black dashed curves here. So it would try to interpolate one spline over the wave's maxima and one over the wave's minima. And then it basically just takes the average of these two splines, and then it would reperform that whole procedure on this new curve. So it would do this again and again until it converges. So in this diagram, it's basically what the blue curve is what it looks like after 20 iterations. And then after that, you would do some extra processing and computation, and you can get the heart and breathing signals. So the way that they actually collected the data for this experiment was that they set up this special room right here. So the room would have a bed and a lot of other portable furniture. And then they would position the sensor on the other side of the room. So they made all the furniture portable so that you could experiment with different distances from the sensor and see how like the performance changes. So all of the participants had to wear a special shirt. It's called the WWS t-shirt, or the Wearable Wellness System. So the shirt basically contains some contact sensors like an ECG and accelerometer that have actually proven to be reliable at measuring uh, the physical movements and the vital signals. So basically, you'd have the shirt collect the ground truth, and then there would also be a camera that would help with collecting all the physical movements as well. So then the participants, they would perform various activities in the room, like sitting down or eating or lying down. So basically the lying down would simulate how a person would act after falling down. So they basically just pretend to be unconscious after falling. And then they would simulate falling in different directions on the mattress. And they'd also do some experiments where they'd have extra people in the room just to see how the sensor would perform when there's extra interference. So the sensor will collect these cardiac and respiratory signals through a transmitted wave that would be bounced off of the subject's chest. And then they would obtain a movement signature with all the Doppler effect stuff. So what's next is that they would train a classifier that could distinguish between a fall and a no fall situation in the movement signature. So they ended up using both a supervised learning approach and an unsupervised learning approach. So basically the difference between supervised learning is that supervised learning needs labeled data while unsupervised learning doesn't. So one problem that they encountered was that they couldn't actually get actual representative falling data, since they would need to have old people, which is the target audience, fall down and again on a mattress, which probably wouldn't be ethical. So they kind of worked around this problem by having two groups of subjects of different ages. Then they have one group be the training group and the other group be the test group. And then, so this would be a way that they could check how the classifier would generalize to people of different ages. So in the supervised learning approach, they would train a support vector machine, which is this left graph right here. So it's basically just a linear classifier that could separate between two types of data. In this case, it would be the fall data and the no fall data. And they'd also do an unsupervised learning approach. So in the unsupervised learning approach, they would train a model that would treat not falling as a normal situation and any fall as an anomaly or an exceptional situation. They didn't really go into much detail in the paper about how they did this, but my guess is that they probably use some type of clustering algorithm. So they probably just grouped together all the no fall features since most of the features were no fall, and then any feature that fell outside of this cluster, like an outlier, so it would be this like red dot up here. So they would classify that as a fall, basically. So onto the results. So first here we can see the results of the vital signal data collection. So in these graphs, the blue graph is the ground truth collected from the camera and the shirt. And red is the data collected from the smart sensor. So it turns out that the sensor was actually pretty accurate. It achieved around 85% accuracy. You can see like that the period of the oscillations lines up pretty nicely between the ground truth and the collected data. So indicating that the heart rate and the breathing rates were pretty similar to each other. One thing that they noticed was that for some of the activities, the measurements were way less accurate. So you get like really good accuracy on activities like sleeping or lying on the ground motionless. Um, so when you're basically unconscious or not moving at all, so it'd be these green and blue curves at the top here. Then you get like a slightly worse accuracy when you're doing a conscious but stationary activity like watching TV. And then you get way worse accuracy when you're doing something with more movement like eating or cooking. So basically they found that chest movements will really mess with the measurements. So when you're eating or cooking, your chest is moving quite a bit, and that really tanks the accuracy. They also found that the orientation and the distance with respect to the sensor will also affect the performance. Like the sensor won't perform as well if you tilt your body away from it or if you're too far away from the sensor. So sometimes if you're too far away, it actually becomes more difficult to distinguish the heart and the breathing signals during the signal decomposition as well. However, they found out that having extra people in the room won't really ruin the accuracy too much as long as everyone is a few feet apart from each other. So in the left diagram right here, we have a motion signature captured by the sensor. So this red peak right here would basically be a fall, and the rise before it would be an accelerating walk. So this would be a simulation of how it'd be like before a person would actually fall down. So the acceleration is probably due to the person like trying to catch themselves before falling. So they found out that the peaks are actually pretty easy to identify in the signatures, and the classifiers ended up getting pretty good accuracies. Like the unsupervised method actually did better than the supervised one. It got over 90% accuracy as long as it got enough training time.
The second research paper, this paper focuses on measuring the pulse rate using long range imaging photoplethysmography. This technology is often referred to as IPPG. Currently, there exists traditional PPG technologies that are non-invasive and measure changes in light absorption related to cyclic and volumetric changes in blood volume to monitor heart rate. And this is exactly what we see in smart watches and smartphones today, where you touch your finger to your phone's built-in camera to monitor your heart rate. But keep in mind here that there is physical contact required to measure the heart rate. The motivation behind the second research paper is contactless sensing, and that is exactly what connects the first research paper and the second research paper. Just like the traditional PPG, IPPG is non invasive, but in addition, requires no physical contact. Rather, IPPG sensing is performed at some distance away from the patient or the participant who's part of the experiment. Now, since there is no physical contact, it is logical to test the impact of distance between the IPPG sensing device and the patient. So, most of the literature that's available to us today reveals that they use a, a range of zero point zero 0.05 meters to 3 meters at the most. However, the goal of this paper is to extend the upper range to over 150 meters. Um, Papers that are available to us right now conduct these experiments in controlled light settings where they limit the total intensity of illumination that's provided to the IPPG sensing device. However, to determine if these long distance measurements could be improved upon, this paper replicates the experiment outdoors, where they use the natural sunlight as the source of illumination. And it is hypothesized that the natural sunlight would contribute to the improvement in these measurements. I'll now pass on to my teammate who is going to highlight the methodology.
Hello everyone, my name is Shiva Mutreja and I'll talk about the materials and methods in the long distance imaging for pulse rate estimation. First, I'll talk about the data collection setup, then I'll talk about how the blood volume pulse rate is estimated from the video using the two techniques. Then lastly, I'll talk about how the signal to noise ratio is extracted. So the image on the right shows the setup for data collection. There are a total of 27 participants in this study with large variation in age group, gender, and appearance. The age group varied from 17 to 47 with the equal number of participants from both genders. And the appearance also varied. And this is important because we are concerned with gathering video of the face and shoulders. So the appearance variation was from different variation in facial hair, and some participants also wore glasses, etc. All of the experiments were done in a highly illuminated outdoor environment where sunlight was the only illumination. Even though the illumination was high, there was a lot of variation both across experiments and also during individual experiments. Thirdly, the type of lenses and cameras used were telephoto lenses, which are medium to long range lenses. These were essential because the distance between the subject and the camera was varied from 25 to 150 meters. As you can see in the image, a uniform gray background was maintained so as to eliminate any background movement noise which could interfere with the results. Lastly, we also need ground truth ECG data to compare our results from the RGB video. For this, we use Biosemi's active 2 electrode ECG sensor, which is strapped around the waist of the subjects to get the ground truth pulse computation. And the output of this ECG sensor is then synchronized with the video to get the final results. So the two main techniques the paper talks about is the ICA, or the independent component analysis, and the chrominance techniques. Both techniques start by extracting and averaging the RGB time series from the video, which is essentially separating the three channels of the video of each pixel and then averaging all the pixels of every frame. So you have three time series signals. The signals are then normalized to zero mean unit variance. Now we'll talk about the ICA, or the independent component analysis technique. So the idea here is you're trying to separate the RGB signals in a source space such that the components you get are representative of different variation sources in the video. So you do blind source separation approach using the extended Infomax algorithm, which decomposes the RGB time series into different source components. And we know that the blood volume pulse signal is the component which contains the largest ratio of peak power and is to the power in the other frequencies. All other signals would correspond to the noise in the video. The second method is the chrominance method, which assumes that the illumination in the video is white light and the participants have a uniform skin tone. And these assumptions are fairly widely applicable, and so we can use this method. Based on these, we come up with two chrominance or color tone vectors, which are applicable for skin tones in general, and they're evaluated for a large range of different skin tones. So the first component is 3R minus 2G, which is essentially a color tone, and similarly we have another color tone Y. These color tones are then combined further to give a chrominance signal, which is nothing but denoted by S, which is X minus alpha Y, where alpha is nothing but the ratio of the standard deviation of X and Y. These components are then combined in the way I just described to extract the BVP signal. As you can see in the graphs to the left, the noise in the signal increases significantly with distance, and it becomes harder and harder to extract the underlying signal as the distance of the camera increases from the subject. Now lastly, I'll talk about how extracting of signal to noise ratio happens. It is important to understand that in a long distance contactless scenario, it is important to know up to what distance the method is applicable, and for this we need to be able to compute the signal to noise ratio. So as we saw in the graphs above, the signal to noise ratio increases with distance independent of the method. So it is crucial to estimate it, and we use the following method for estimation. Once we have the BVP signal from the RGB signals, we first compute the 512-point FFT, or the fast Fourier transform of the extracted signal. From this transform, we identify the peak corresponding to the heart rate and its first harmonic. We are able to do this because we are also simultaneously computing the ground truth ECG data, which gives us the peak frequency. Thirdly, once we have the peak and its first harmonic identified, we can compute the power in the frequency domain around these frequencies in a small neighborhood. This is nothing but the power corresponding to the truth signal or the BVP signal. Second, we compute the power in the rest of the frequencies, which is nothing but the energy corresponding to the noise. And as we know, the signal to noise ratio is computed by the power in the signal divided by the power in the noise. So if we take the ratio of the above two quantities, we get the SNR, which is a good measure of whether or not we are able to successfully identify the BVP signal from the extracted signal. So that's about it.
Variable of this experiment is the distance between the IPPG sensing device and the patient or the participant. The data that was collected during experimentation is compared using a number of statistical methods over varying distances. Here, the authors use the mean absolute error, the signal to noise ratio, and a correlation between the ECG values and the IPPG values. The graphical representations of these statistical methods have some trends. One, there is a higher error at longer distances, and two, there are larger errors in chrominance based methods over ICA based methods. Now, given the inherent advantage presented by the IPPG's ability to make measurements from a distance away from the patient or the participant, it was worthwhile extending the upper range of the distance to over 150 meters in comparison to the 3 meters that's currently being used in the literature that's available to us today. And in addition, as hypothesized, when imaging at such long distances, illumination was critical. It was essential to use the natural sunlight to improve the accuracy in comparison to the source of illumination that was available indoors and that limited the intensity of the illumination. However, there are certain limitations. In the outdoors, the lighting conditions are variable and cannot be controlled. These conditions change with changes in cloud cover or changes in wind gusts and increase or decrease in visibility. We have a few discussion questions that might result in societal implications. Due to the contactless nature of communications in sensor networks, will misuse or privacy concerns restrict people from taking advantage of the full benefits from the system? How can these concerns be addressed? Now, here, since the data that we're talking about is personal health data that might include medical records, you wouldn't want it to be available to the public. Now, knowing that your health data is vulnerable to attacks and tampering, how do you think the people would respond? Or how do you think they would make use of such a technology if it were to be made available to the public? And the second question here we have for you is, as this data will be sent to different people at different places for diagnosis, who will have the responsibilities and liabilities for the data collected from a person? I mean, given the data that's at stake here, you would like to avoid eavesdropping or prevent forgery of medical data that might lead to incorrect diagnosis. So, what are your thoughts? Or do you guys have any questions?